SwayamPrabha. Digital India. Educated India.
In this lecture, we will discuss about how to initialize MD simulations. So, this diagram shows various steps involved in MD simulations. So, the first thing to do is to generate the trajectories of the system. This basically means getting the position velocities as a function of time for all the particles. So, that is what we mean by the trajectories. Once we have these trajectories, we can analyze these trajectories to calculate thermodynamic properties, structural, dynamical properties. Now, we have looked at various means of generating these trajectories, which are nothing but solving the equations of motion using some discrete methods. And this generation of trajectory itself involves many other steps. For example, we need to first initialize the simulations, and then we need to do what is known as this equilibration and then production. So, this is a production run in which we actually accumulate properties of our interest. So, in this particular lecture, we will focus our attention to what is this initialization and how to do this. Now, our starting point in MD simulation was the equations of motion that tells the dynamic evolution of the system. So, in the Lagrangian framework, you can show that the equation of motion is a second order ODE, which relates the acceleration to mass, which is nothing but Newton's second law. And this force is obtained by specifying a potential energy function, which may include inter and intramolecular interactions. Now, in order to solve this second order ODE for each particle, we need a set of initial conditions, namely the position of all the particles at time t equal to 0 and the first derivative of the position, which is the velocity at time t equal to 0 for all particles 1 to n. So, these are the initial conditions that we need to specify before we can run the MD simulations. So, in this particular lecture, we will see in detail how to assign position and velocities for all these particles in the simulation. We will illustrate these methods for a cubic simulation box in 3 dimensions, which has an edge length of L. If you want to look at other shaped simulation box, the algorithm has to be accordingly modified. The most simplest way of assigning particle positions inside a simulation box is randomly assigning particles inside a simulation box. It can be done by writing the first particle's x position as the edge length of the box multiplied by a random variable r1, which is uniformly distributed in the range of 0 to 1. Similarly, the first particle's yth position, which is another degree of freedom, independent degree of freedom, can be also assigned using another uniformly distributed random variable. Similarly, for the z component of the first particle can be assigned using a random number. So, by using 3 uniformly distributed random number, we can specify the position of a first particle inside a simulation box. Now, we can actually iterate this over for many other particles. When you go to the second particle, third particle, etc., you approach the initialization exactly like this by every time calling 3 sets of random numbers. However, we have to be careful when we use random initial configuration like this, because when we try to put a particle inside the simulation box by this random assignment, the particle might overlap with the particles present already in the simulation box. So, let's say you put first particle there, the entire box volume is available for the first particle's position, whereas when you put the second particle, we have to ensure that it does not overlap with the first particle which is already present. Similarly, when we assign the position for the third particle, we have to ensure that the third particle does not overlap with the first and second particles which were already put in. So, we can generalize this approach to say that whenever we assign a random initial position for ith particle, we have to check for the overlap of the ith particle with 1 to I minus 1 particle which were previously assigned in the simulation box. Because of this overlap being an issue in the random initial configuration, this method only works when you are looking at low density. When you try to use this initial condition at high density, what will happen is we will not be able to find the right position for the molecules, because most of the time they will overlap with the existing molecules. So, this random initial configuration or the random initial positioning will only work when the system density is low. Now, for high density system close to a liquid like state or high density system, the other approach to assign particle positions initially is by using a lattice. In this method, we can ensure that no two particles overlap. The way we do that is, we take an FCC unit cell and we replicate this unit cell in space to fill a desired number of particles in a unit volume. Again, we are basing, our basis here is the simulation box of cubic shape of edge length L. So, now to put the particle, instead of randomly assigning, we are going to just assign them using a unit cell, and the unit cell can be conveniently taken as an FCC unit cell, and this FCC unit cell will have a density of n by v, or this n by v is the density that we want to have in the simulation box as well. So, what is a unit cell? The unit cell basically describes the location of the smallest number of particles needed to define the symmetry. So, this FCC means face centered cubic unit cell. So, it has a certain symmetry, and an unit cell will have the specification of the location of the smallest number of particles needed to ensure FCC symmetry. Now, for an FCC unit cell, the edge length is small a, and then we will note that the density of the unit cell is basically the density of the entire lattice that we construct using unit cell by replicating it in space. In an FCC unit cell, the density is given by number of particles in the unit cell divided by the volume of the unit cell. Since the lattice is cubic lattice unit cell, the volume is given as a cube. Now, for an FCC unit cell, this number of particles per unit cell is given as 4. What it means is, in an FCC unit cell, we can assign position for at least minimum 4 particles, and the position vector of these 4 particles are given as one at the origin, second one in the YZ plane, and the third one in XZ plane, and the fourth one in XY plane. And the positions are given by these 4 vectors. Pictorially, these molecules are shown in this particular cubic box. So, this is an FCC unit cell, and the edge length of this unit cell is A. So, we take a coordinate system x, y and z, which are all orthogonal to each other. The first particle is at the origin, that is this, and the second particle is in the YZ plane in the center of this particular face, and the third particle is in the XZ plane, that is right here, and then the fourth particle is in the XY plane, which is here. So, now what we can do is, in one unit cell we are able to position 4 particles. Now, we can replicate this FCC unit cell in space. We can go and we can replicate this unit cell in x direction, y direction and z direction, and then we can actually have as many number of particles that we want in the system. And the idea here is that the density that we want to have in the simulation box is given by the density of the unit cell itself. So, this is the definition for the density of the simulation box, whereas this is the density of the unit cell. So, now this is shown here, this is the FCC unit cell, and then if you start replicating, you will get this kind of a lattice, which is known as FCC lattice. You can see there are atoms in the corners of the coordinates, and also there are atoms in the center of the faces, each faces. So, all these dark circle here are the atoms at the faces of the cube here, and those white circle are at the edges of the cube. So, now what we can do is, since the replicated lattice has the same density as that of the unit cell's density, and for unit cell density this is n by a cube and n is 4. So, we can equate these two, and then from here we can solve for number of particles in the simulation box, and it goes as 4 times L cube by A cube. So, this L cube is nothing but volume of the simulation box. A cube is the simulation of is the volume of the unit cell that we consider. So, then if I define M as L by A, we can show that the number of particles we can put in a simulation box goes as 4 times m to the power cube, whereas m here is L by A. In other words, this is the number of unit cells in each direction that we replicate, the unit cells. Now, by looking at the different values of m, we can see the number of molecules that can be used in the simulation box. If you choose m is equal to 2, n becomes 32. If you choose m is equal to 3, that means we are replicating FCC unit cell of 3 unit cells in each direction. Then we are able to build or assign 108 particles in the simulation box. And then if I use m is equal to 4, I can use 256 particle in that particular simulation box, and then the list goes on. So, when we use this FCC lattice as a unit, as an initial condition, we have to always decide particles in this number range. It has to conform to this particular relationship between the number of repeating units and the number of molecules in the system. Now, in the simulations, what we like to do is, first we choose the number of atoms that we need to simulate. So, this will be constrained by based on the computing power that we have and the system size requirement. So, we have to decide first of all whether I want to do a simulation of 108 particles or 500 particles or 864 particles. So, that is something that we have to decide based on the computational resource available. Then we also have to specify the thermodynamic condition, namely the density at which I want to do the simulations, and the density is given by number of particles per unit volume. So, now I know the number I have chosen based on the computing power requirement, and the density is something fixed based on the thermodynamic condition that we want to study. From this, we can find the volume of the simulation box that we need. From the volume, we can find L, because V is nothing but L cube, and then we can find the edge length of the FCC unit cell as L by M, and M is also known because if N is known, and N should be related to 4 times M cube. The moment I say what is N, the number of unit cells in each direction is also known. So, using this, we can find what is the edge length of the unit cell. So, that means for a given particle number and density, we are able to basically find out non-overlapping lattice positions for the atoms, and those unit FCC lattice will have an edge length given by L by M. L is obtained from rho is equal to N by V. N is known, rho is known, volume can be found. From volume we can get the L, whereas this M can be obtained from the relationship for FCC unit lattice, which is N is equal to 4 times M cube. So, now we can ask what is the maximum density that we can pack in an FCC lattice. So, to see this, if you think about this particular lattice, and if you start making this particle larger and larger, each one of them, at some point of time they will start touching, and then you can see a relationship between the edge length of the unit cell to the diameter of the particle. So, at contact you will see that the edge length will be equal to square root of sigma. Sigma here is the particle diameter. Then we calculate the maximum density that is possible, which is N by A cube. Remember, rho max here is N by A max cube, and this A here is given as square root of 2 times sigma, and then when you substitute, you can see that the rho max is given by square root of 2 divided by sigma cube in a dimensional unit. If you are willing to work with the non-dimensional rho max, this will be simply square root of 2, which is 1.414. So, this is the maximum density that is possible to pack, which would be nothing but an FCC lattice, where the particles are just touching. You can also calculate the maximum volume fraction from the maximum density, which is nothing but the volume of the particle times the rho max, and this comes out to be about 0.74, which is known as the close packed limit. So, in FCC lattice, you are able to pack as high as a volume fraction of 0.74 and anything below that. So, in assigning particle positions, we use either of these two methods. At low density, one can conveniently use a random initial configuration, whereas at moderate and high density, because of the overlap issue, we can use a FCC based lattice, which allows the packing to be as high as possible. The second objective is to assign initial velocities for each particle as well. So, here again there are multiple ways to do this. One way is to assign the components of the velocities v1x, v1y and V1s z as a independent components of the velocity using a set of random numbers r1, r2, r3. All these r1, r2, r3 are the uniformly distributed random number in the limit of 0 to 1. But when I do this transformation of 1 minus 2 r1, this basically makes the velocities to be in the interval of minus 1 to plus 1. To see this, the minimum value of r1 can be 0 and the maximum value of r1 can be 1. So, that is the limit of this random number. So, when I substitute that here in this equation, this will tell me that V1x can be at the max. So, now we saw how to assign initial positions for the particles in the simulation box, either using a random initial configuration or using a lattice to assign positions. The next objective for us to initialize the simulation is by assigning the initial velocities. There are a few methods by which we can assign initial velocities. The most simplest approach is randomly assigning velocities. To do this, we take random numbers r in the interval of 0 to 1 and then we assign the first particle's x component of the velocity as 1 minus 2 times r1. The reason why we do that is, since r goes from 0 to 1, if you do this linear transformation of this random number r, you will see that this v1x goes in the limit of minus 1 to plus 1. So, the velocity can be either positive or negative in the interval of minus 1 to plus 1. To see this, if r is equal to 0, this transformation will say that v1x is going to be plus 1. The other limit of r is 1, in which case the v1x will be 1 minus 2 into 1, that is minus 1. So, we can see that as the random number goes from 0 to 1, the velocity will go from minus 1 to 1 when you do this linear transformation. So, we assign the first particle's x velocity by this expression, and we repeat the same thing for the y component, z component of the first particle velocity using other random numbers r2 and r3, and we repeat this for all the particles in the system from 1 to n. So, essentially after doing this algorithm, we would have generated velocities in the interval of plus 1 to minus 1 for all the particles. Now, because we have assigned randomly the velocities, we have to ensure whether the overall linear momentum is 0 or not. So, we want to ensure the condition that the linear momentum p, which is defined as sum over 1 equal to n, sum over I is equal to 1 to n, mi vi should be equal to 0. But since these velocities are randomly assigned, we may not be able to get exact 0 linear momentum, total linear momentum. So, in order to adjust the velocities such that the linear momentum goes to 0 at time t equal to 0, we have to adjust the randomly assigned velocities. The way you do that is, you take all the velocities that we have assigned and then sum all these velocities for x component and then divide by the total number of n, and this will give you the excess amount that needs to be subtracted from the old velocities. So, when you do this operation, you get a new set of velocities, and this, when you substitute for the linear momentum, you can show that the linear momentum goes to 0. This operation has to be done for viy and viz also. So, this approach basically assigns velocities in the range minus 1 to plus 1 to start with, and then we correct these velocities so as to ensure the linear momentum is 0 at t equal to 0. And we already noted that the MD simulation with the periodic boxes conserves linear momentum throughout the simulation. Now, the other approach to initialize the velocity is by sampling velocity from a Maxwell-Boltzmann distribution. So, the Maxwell-Boltzmann distribution of velocity is given by this expression. You can see it is a Gaussian function and it depends on the temperature, mass of the particle, and kb here is the Boltzmann constant. So, now we should be able to sample a random number based on this particular distribution, and that random number will be a normal random variable with a 0 mean and a standard deviation given by proportional to square root of t. So, the way you can apply this particular method is, first draw a uniform, first you draw a unit random variable with the 0 mean and unit variance, and let us call that as chi, and then since we want the velocity to have a variance of square root of kbt by mi, and then we scale the velocities. So, this is a unit random normal variate, and then we multiply this by this standard deviation factor of square root of kbt by mi, and the product of these two number will be the random variable velocity vix, which will have a 0 mean and standard deviation. Now, the question is, how do we generate the unit normal random variate psi here? So, there is a popular method known as Box-Miller method, which basically generates a sets of unit normal random variate. The way it is done is, you first generate two uniformly distributed random number eta 1 and eta 2 in the range 0 to 1. This is a uniformly distributed random variable. Once we have eta 1 and eta 2 generated, then we can calculate the unit normal random variate psi 1 and psi 2 by using this mathematical operation, that is square root of minus 2 ln eta 1 cos times 2 pi eta 2. So, we use this eta 1 and eta 2 to get psi 1, and similarly we use eta 1 and eta 2 to calculate psi 2. So, for every sets of random variate eta 1 eta 2, we are able to get 2 unit random normal variate. Once we have this eta 1 eta 2, that can be substituted here to get velocities for each component. So, in this approach, we are basically assigning the initial velocities based on an equilibrium velocity distribution itself using Maxwell-Boltzmann distribution. Another approach would be to create initial velocity distributions in the interval some minus Vx to plus Vx, or Vmax, minus Vmax to plus Vmax. This velocity maximum can be obtained from a Maxwellian distribution. The Maxwellian distribution looks something like this, and then you can find some Vmax plus and Vmax minus, and then you can generate a random number in this limit. So, in order to do that, all you need is you call a uniformly distributed random number r, and then you do 1 minus 2r, and then multiply this by Vmax. So, when we do this linear transformation, you will see that this V1x will have a range from minus Vmax to plus Vmax, and this can be repeated for other components and all the components of the other particles also. In this approach also, we need to ensure that the linear momentum is conserved. So, to do that, you again take the average per particle velocity, and then you subtract this residual amount from the old velocity, and that will assign a new set of velocity. So, this new velocities would have a distribution from minus Vmax to plus Vmax, at the same time also satisfy the condition of 0 initial linear momentum. Now, when we do NVE ensemble, we will be required to fix the number of particles, volume, and the energy of the system. So, number can be chosen based on the availability of computational resources, and volume can be decided based on the density that we want to operate once we know the number of particles. Now, fixing the energy is little important. Now, we have already said about initializing the position and initializing velocities. Once we have done this, we have also ensured that the initial energy is also kept constant, because the kinetic energy is related to the initial velocities, and this potential energy depends on the initial positions. So, once we have set the initial position and initial velocities, we have essentially set the system's energy too. However, it may be that we want to do a simulation with a particular energy scale E. Let us call that as ED. So, this is the energy that we want the simulation to be performed at, whereas this random initial positioning and velocities would have given a different energy which may not be equal to the desired energies. And we also recollect that the total energy can be written as a sum of kinetic energy and potential energy. Similarly, in the desired energy also, we write the total desired energy would be sum of the desired kinetic energy plus the potential energy. So, now we do not want to change the initial position, so that the energy of the potential energy remains the same, but we can scale the temperature such a way that the Kd can be adjusted, so that the total energy becomes equal to Ed. So, in order to do that, we solve for the required kinetic energy as the desired total energy minus the potential energy. I am talking about all that at time t equal to 0. Now, we also know from the statistical mechanics that the kinetic energy is related to sum of the square of the velocities. So, that means velocity is proportional to square root of k. So, now what we can do is to maintain a desired kinetic energy in the system, we take all the velocities we have assigned in the initial times and then scale by a factor which is equal to square root of Ed minus Eu divided by E minus U. So, what this basically means is the square root of function is basically Kd divided by K. So, this is a kinetic energy corresponding to the initial velocity, but this is the kinetic energy that we want the system to have so that the total energy can be Ed. So, this scaling of the velocities proportional to the square root of Kd by K will set the total energy at the desired level, even though we would have started with some initial random position and random velocities. So, initialization means not only simply assigning the positions and velocities, but also ensuring the linear momentum is conserved and the total energy of the system is fixed at the desired level. So, with that we summarize that in MD simulations we need to initialize the positions and velocities so that the equation of motion can be integrated numerically with certain finite difference algorithms. As far as the positions are concerned, we can either assign random initial positions which works for low density. At high densities or moderate densities, we often use a lattice to assign the particle positions. Now, the velocities are generally assigned either randomly or sampled from an equilibrium Maxwell-Boltzmann distribution. For NV simulations, that is microcanonical ensemble, the velocities has to be scaled such a way that the energy can be fixed and the total linear momentum is kept at 0.